So, in the previous videos we developed 32 three-dimensional point groups. Now, there are different ways of classifying these point groups into different classes. One very common classification is the 7 crystal systems. So, 7 crystal systems are nothing but 7 different types of point group, and what is used as a basis for this classification. So, 7 crystal systems. So, 32 point groups will be classified into 7 crystal systems, and the basis for classification is the characteristic symmetry. That is, point groups having certain symmetry will be put into certain crystal systems. So, we will do it, and this one by one for the 7 crystal systems. So, let us start with the names of the crystal system. So, the first system we will list is Triclinic, and the characteristic symmetry for that is either a one-fold axis, which actually means no symmetry. So, if a crystal has no rotational symmetry, if the point group has no rotational symmetry, it will be having a one-fold axis, or if it has just a center of inversion, 1 bar. So, any point group having 1 or 1 bar as its symmetry operation will be considered, and nothing more, nothing beyond this, because there are a lot of, when we developed, there were a lot of point groups which were having the center of inversion. So, we will not consider all of them as triclinic, we will consider the ones which are triclinic is which has only 1 bar as its symmetry operation and nothing else. So, either no symmetry or 1 bar symmetry. So, you can see from this that there are only 2 point groups which we developed will qualify, 1 or in the Schoenflies notation C1 or 1 bar, which is in the Schoenflies notation is Ci, I for inversion center. The second crystal system is monoclinic. Here the characteristic symmetry is 2 or 2 bar, and you are now well familiar that 2 bar is nothing but a mirror plane. So, the point groups which will belong to the monoclinic system will be 2 or C2, M or CS, and 2 by M, which is C2H, two-fold with a horizontal mirror. That is the Schoenflies notation, C2H. Then we come to the third crystal system, orthorhombic. Orthorhombic requires 3 perpendicular two folds, 3 perpendicular two folds or 2 bar. The point groups which will belong to this crystal system is the dihedral group 222, in the Schoenflies notation D2 or MM2, which is C2V, or finally MMM. So, this has 3 orthogonal mirrors as well as 3 orthogonal two folds in Schoenflies notation T2H. Then let us come to the tetragonal point group, tetragonal crystal system. Here the requirement of symmetry is 1, 4 or 4 bar axis. So, the point groups will be 4 obviously will qualify, 4 bar will also qualify, 4 bar in Schoenflies notation is S4. Then you have the dihedral group 422. Then you have 4-fold with vertical mirrors 4 mm. C4V in Schoenflies, V indicating the vertical mirror with the 4-fold axis. And you have 4 by M, it's C4H for horizontal mirror, 4 bar M2, Schoenflies notation D2D, D for diagonal mirror with the dihedral point group 222, so D2D. And finally 4 by M, mm, which is D4H. So you can see that 7 point groups belong to the tetragonal crystal system. And we come to the trigonal system, which is characterized by one 3-fold axis. So the point groups which will belong to this will be 3 bar, 3 2, 3 m, and 3 bar m. The corresponding Schoenflies notations are C3, 3 bar is C3I. Let me write it, let me not use brackets. So C3, C3I, 3 2 is D3, the dihedral group, 3 m is C3V, and 3 bar m is D3D. Hexagonal, characteristic symmetry 1, 6 or 6 bar. So we had 6, which is C6, 6 bar, which is C3H. Note that the 6 bar axis is a 3-fold axis with a horizontal mirror. So that is what is reflected in the Schoenflies designation. 622, the dihedral group D6, 6 mm, C6V, 6 by M, C6H, 6 bar M2, D3H, 6 by M, mm, D6H. And finally, the cubic point groups, the characteristic symmetry is 4 3-fold axes, and we have seen that there are 5 point groups which qualify, which has this property of having 4 3-fold axes, and they are 2 3, the rotation group of tetrahedron, 4 3 2, rotation group of the cube, which is also the rotation group of an octahedron. So Schoenflies uses O for its notation. Then M3 bar, which is TH, and you have complete symmetry of tetrahedron, which is 4 bar 3M, Schoenflies notation TD, and complete symmetry of the cube, M3 bar M. So, in Fly's notation OH. So, in this development you can see that the crystal systems are nothing but classification of point groups. 32 point groups have been put in these 7 bins based on whether they have these characteristic symmetry or not. So, crystal system is not really defined by the axial relations, but by these symmetries. So, that point is important. Having said this, of course, if the crystal belongs to a particular crystal system, one can always select unit cell which satisfies those relations. So, let me take an example. So, A equal B equal C and alpha equal beta equal gamma is equal to 90 degree. This is considered to be cubic crystal system, but now we are saying that the crystal system is not defined by this relation, but by this relation, that crystal system should have 4 threefold axes or only these 5 different point groups. If the crystal has these 5 point groups, it can be considered as cubic. But once it is considered as cubic, one can select out of many possible unit cells, one can select a unit cell in which this relationship will be satisfied. So, that is what is considered as the conventional unit cell. So, lattice parameter relations are satisfied by conventional unit cells. Thank you.